Howdy. Today in class we talked about the algebraic technique of partial fraction decomposition. And I explained it as the idea that we can take a complicated fraction, p of x over q of x, a complicated rational function, and break it down in terms of its factors. By writing it as the sum of of fractions with the appropriate numerators. What I wanted to do now is to go through the details of how that works with two examples. And I want to consider the examples first in isolation without worrying about calculus for a moment. I want to consider just the fraction x over x squared minus 5x plus 6. And I want to consider how we might break this down into partial fractions. First, we're going to observe that the power of the numerator is strictly less than the power of the denominator. So this is actually needed in order for our partial fractions to make much sense. If it is not the case, we could still do it, but it gets kind of yucky, and it is preferred that you first divide if your numerator has a degree that is larger than or equal to the degree of the denominator. So that's the first thing. Then, having said that, we're now going to appeal to the age-old concept that factoring is our friend. And we're going to factor the denominator as x minus 3 times x minus 2. And this gives us a clue as to what the partial fractions will be. One of them is going to be a over x minus 3, and one of them is going to be b over x minus 2, for some constants a and b. Notice that each factor in my partial fraction decomposition led directly to a term in that decomposition. Now, the question is, how do we determine the values of a and b? And there are a couple of methods that are useful. I'm going to illustrate one method here, and that's going to be the method of clever substitution. And then I'll illustrate the second method in my second example. Clever substitution is going to start by clearing fractions. I'm going to take my decomposition, and I'm going to multiply both sides by the common denominator, which is x minus 3 times x minus 2. And when I do, then on this side, everything goes away, leaving me with x. And on this side right here, in the first factor, the factor of x minus 3 cancels, leaving me with the factor of x minus 2. And the second term, the factor of x minus 2 cancels, leaving me with a factor of x minus 3. So I have this equation now. X is equal to a times x minus 2 plus b times x minus 3. And this equation is going to have to be true for every value of x in order for this decomposition to be valid. So the trick is, a and b will have specific values, but those values must hold for all values of x in order for this to be a true equation. So, which values of x would we like to consider? I would like to consider values of x that make these various terms disappear. So I'm going to, in the first instance, choose x equals 2 as a value to substitute into this equation. And when I choose x equals 2, then I get that 2 is equal to a times 0 plus b times negative 1. Well, that means that b is equal to negative 2. And in the second instance, I'm going to choose the value x equals 3. And when I choose x equals 3 and substitute into the equation, I get 3 is equal to a times 1 plus b times 0, so a is equal to 3. And now I've got my values of a and b simply by appealing to some clever substitution. Let's write our partial fraction decomposition. What we are saying is that x over x minus 2 times x, I wrote it backwards, x over x minus 3 times x minus 2 is in fact equal to 3 over x minus 3 plus 2 over x minus 2. Now you'll notice in this case that I happen to get a 3 here and a 2 here, but that is a coincidence. How do I know if this is actually correct? Well, I would know that this is correct by checking it by adding fractions like we have done for a really long time. I can get a common denominator by multiplying the first fraction by x minus 2 over x minus 2. And I can get a common denominator by multiplying the second fraction by x minus 3 over x minus 3. And that gives me 3 times x minus 2 plus 2 times x minus 3. Excuse me, there's a negative 2 that I missed here. Yes, b was negative 2. And notice that when I caught that because I could look ahead and see that when we combine these terms right here, I'm going to take that minus 2 and make that minus 2 also. There we go. That's better. That when we combine these terms right here, it should be the case that I get 3x minus 2x is equal to x, minus 6 plus 6 is equal to 0, and we have a winner. Now, here's how this would help us with integration. Let's suppose that I need to integrate the integral of x over x squared minus 5x plus 6 dx. Some different ways I could try to approach it. I could try to let u equal the entire denominator, but then du is 2x minus 5. That's not exactly right. So then I might try a partial fraction decomposition. Suppose that I take this x over x squared minus 5x plus 6, and I discover that it is exactly equal to 3 over x minus 3 minus 2 over x minus 2. Well, in that case, I can integrate term at a time easily and get 3 natural log of x minus 3 minus 2 natural log of x minus 2, and I'm done. Of course, you got to be careful because answer keys will often use log properties to rewrite. So you could see this answer, or you could even see this answer right here. So just be careful about that. Any one of these three, of course, would be acceptable. So that's the partial fraction decomposition, and the method that we used to find a and b here was clever substitution. Having cleared the fractions, I came back and I chose values of x that would zero out the particular terms that I was presented with, so that I could solve for a and b directly. I'd like to give a second example that will illustrate a second method. Suppose that I want to decompose the fraction x plus 1 excuse me, let's go with x plus, yep, no, x plus 1 works. X plus 1 over x cubed plus x. And what I want to do now is to write this in terms of its partial fractions. Well, again, I check that the degree of the numerator is smaller than the degree of the denominator, and it is. And again, I factor. And when I factor, what I find is very interesting, is that my second factor right here is an irreducible quadratic. Or you might call it a prime quadratic. And that irreducible quadratic now, I'm not going to be able to factor unless I want to go into complex numbers, which I do not. And so I'm going to have to write the decomposition in this way. I'm going to write it as a over x for the first factor. For the second factor, it's entirely possible that this irreducible quadratic here could have a remainder that includes x. So that for the irreducible quadratic, I'm going to write its numerator as potentially bx plus c. It may be that b is 0, but potentially bx plus c. So that is the slight variation that we have here with the irreducible quadratic. What if I have a higher power? Well, the good news is that although it's not entirely obvious all the time how to find it, it is always possible to factor a cubic or higher into irreducible quadratic invariant factors. Well, so this time we're going to find the values of a, b, and c by a slightly different technique. We're going to find it by equating coefficients. I'm going to begin by doing the same thing that I did with the other method, and that is to clear the fractions by multiplying both sides by the common denominator. When I multiply both sides by the common denominator, we write it like this over here. Then we cancel and we get x plus 1 over here. And on this side, the factor of x cancels in the first term, giving me x squared plus 1. And the factor of x squared plus 1 cancels in the second term, giving me x times bx plus c. Well, I could cast around for suitable values of x to plug in, and that would certainly work. However, here I'm going to use a different method, and that is I'm going to equate coefficients. If I take the right-hand side and I simplify it a little bit, I get ax squared plus a plus bx squared plus cx. And if I take and compare that to the left-hand side, which is x plus 1, I observe that I now have terms on the right-hand side that are terms in terms of x squared, in terms of x, and in terms of a constant. Keep in mind that this equation is going to be true for particular values of a, b, and c, but must be true for all values of x. And since this equation must be true for all values of x, it is necessary that the coefficients must be equal. Well, on the left-hand side, the coefficient of x squared is 0. And so that means that a plus b, which is the coefficient of x squared, has to add up to 0 x squared. In other words, I have a plus b is equal to 0. And on the left-hand side, the coefficient of x is 1. On the right-hand side, the coefficient of x is c. And so that means that immediately c is equal to 1. And on the left-hand side, the constant term is 1. And on the right-hand side, the constant term is a. And so therefore, a is equal to 1. And since a is equal to 1, it doesn't take too much figuring to discover that b is equal to negative 1. And lo and behold, I have my partial fraction coefficients. I can now say that x plus 1 over x cubed plus x is going to be equal to a over x plus bx plus c over x squared plus 1. And of course I want to check it, and so I will, by the usual method of multiplying top and bottom by common denominators. And when I do and simplify, then I get x squared plus 1 minus x squared plus x all over x cubed plus x, and lo and behold, these cancel to give me what I wanted. Yay! Well, this is how this would work out in terms of integration. Just to review our method. So what I did was to again clear the fractions by multiplying both sides by the common denominator. And then I simply equated coefficients of x squared on both sides, coefficients of x on both sides, constant term on both sides, and so on. And that gave me a system of equations that were easily soluble. Sometimes one method works better, sometimes the other method works better, and that's why we really have the two methods of clever substitution and equating coefficients. How would this actually work out in terms of an integral? Well, suppose I needed to integrate x plus 1 over x cubed plus x. And I observe that no algebra can be done here, no common factors can be canceled, all that good stuff that you look for first. And I also observe that letting u equal x cubed plus x doesn't really get anywhere since du is equal to 3x squared plus 1. So having observed that, now I consider a partial fraction decomposition. And if we go through the work that we just went through up above, then we get this guy right here. Now the first term is going to be easy enough. That'll be a natural log. What about the second term? Well, the second term is not immediately obvious. However, if we remember that division is multiplying by the reciprocal, so that I can distribute my factor of 1 over x squared plus 1 to each term and split up the resulting integral, now things don't look nearly so bad. In the first term, I get a familiar integral. I get the integral of x over x squared plus 1, which we've done several times, and gives me a natural log form. And the last integral is an arctangent form. And we're done. It was not at all obvious when we looked at this integral at first that we would end up with this antiderivative right here. And so these rational functions will often end up with surprise logs and arctangents as a result